The universe did not begin in silence. Its birth was not calm, gradual, or orderly. It did not resemble a sunrise or the ignition of a distant star. The origin of the universe was an event in which time, space, and causality themselves came into existence. Everything that exists today, galaxies, stars, planets, atoms, and even the vast emptiness between them, emerged from a state that modern science can describe only through abstract mathematics and theoretical limits. Approximately 13.8 billion years ago, an event known as the Big Bang occurred. The term is misleading, as there was no single point in space where an explosion took place. There was no center and no edge. Space itself began expanding everywhere at once. In that moment, not only matter was born, but time as well. There was no before, because there was no timeline along which earlier moments could be measured. In its earliest fractions of a second, the universe was unimaginably hot, dense, and unstable. The physical laws familiar today had not yet settled into their final form. Particles appeared and vanished almost instantly. Matter and antimatter were created in pairs, annihilating one another in flashes of pure energy. A tiny imbalance, so small it still defies complete explanation, allowed a fraction of matter to survive. That microscopic asymmetry became the reason anything exists at all. As the universe expanded, it cooled. Energy condensed into particles, particles into atoms, atoms into vast clouds of gas. Hundreds of millions of years later, the first stars ignited. Their light ended the long cosmic darkness that followed the birth of the universe. From that moment, structure began to emerge. Galaxies formed, clusters assembled, and immense filaments of matter stretched across millions of light years. To observers who appeared billions of years later, the universe seemed stable and enduring. Stars were born and died, galaxies rotated, and the laws of physics appeared unchanging. Even the expansion of space seemed slow and insignificant. For a long time, the cosmos gave the impression of permanence. That impression was an illusion. In the 20th century, astronomers discovered that the universe is not merely expanding, it is accelerating. Distant galaxies are moving away from each other faster and faster, as if an invisible force is stretching the fabric of space itself. This revelation marked one of the most unsettling discoveries in modern science. It suggested that the future of the universe might be far more unstable than previously imagined. The mysterious cause of this acceleration was named dark energy. Its nature remains unknown, but its influence appears to dominate the cosmos. Unlike gravity, which pulls matter together, dark energy pushes space apart. The larger the universe becomes, the stronger its effect seems to be. It does not fade with distance. It grows with scale. From this moment on, the question of the end of the universe ceased to be philosophical. It became scientific. If cosmic expansion continues forever, the universe will drift toward a cold, silent fate. If acceleration increases, space itself may eventually tear apart. If dark energy changes its properties, expansion could slow, stop, or even reverse, leading to collapse. Each of these scenarios traces its roots back to the very beginning of cosmic history. The initial conditions set in the first moments after the Big Bang determined not only the formation of galaxies and stars, but also the ultimate destiny of everything that exists. In this sense, the end of the universe was encoded in its birth. Humanity exists within a fleeting interval between origin and conclusion. On cosmic timescales, intelligent life is a brief spark of awareness in an unfolding process billions of years long. Yet within that brief moment, the universe has gained the ability to observe itself. Through telescopes, equations, and theories, humans attempt to understand how the story will end. For centuries, eternity was attributed to the cosmos. The idea that the universe could die seemed inconceivable. Modern science has dismantled that belief. Everything that has a beginning must also have an end. The only uncertainty lies in the form that end will take. Quiet and frozen, violent and sudden, or so strange that current concepts of reality will fail to describe it. The study of the end of the universe is not the study of an instant catastrophe. It is the examination of a slow, inevitable process unfolding over trillions and quadrillions of years. a process that has already begun, even as stars continue to shine and space continues to expand, almost imperceptibly. This is where the journey toward the end truly begins. For most of human history, the universe was believed to be static. Stars appeared fixed in the sky, galaxies were unknown, and the cosmos seemed eternal and unchanging. Even after the discovery of other galaxies in the early 20th century, many scientists still assumed that the universe as a whole neither expanded nor contracted. This assumption was deeply intuitive and completely wrong. The first cracks in this worldview appeared when astronomers began to measure the light coming from distant galaxies. That light carried subtle signatures, known as redshifts, indicating that galaxies were moving away from the observer. The farther a galaxy was, the faster it appeared to recede. This relationship revealed a profound truth. Space itself was expanding, carrying galaxies along with it. The expansion of the universe was not an explosion into empty space. It was the stretching of space everywhere at once. Galaxies were not flying through a void. The void itself was growing between them. This distinction would later prove crucial in understanding the long-term fate of the cosmos. At first, scientists assumed that gravity would eventually slow this expansion. The combined mass of all matter in the universe should, in theory, exert a mutual attraction strong enough to counteract the initial outward motion. The ultimate question became one of balance. Was there enough matter to halt expansion, or would the universe expand forever? For decades, this question remained unanswered. Observations suggested that visible matter, stars, gas, dust, was insufficient to stop expansion. The discovery of dark matter helped fill part of the gap, revealing that most mass in the universe is invisible. Yet even with dark matter included, calculations still could not fully explain the observed dynamics. Then came the most unexpected revelation of all. In the late 1990s, two independent teams studying distant supernovae made a startling discovery. The expansion of the universe was not slowing down. It was accelerating. Distant galaxies were receding faster now than they had been in the past. Something was not merely overcoming gravity, it was dominating it. This unknown influence was given the name dark energy. Unlike matter, dark energy does not clump or form structures. It appears to be a property of space itself, exerting a constant pressure that drives expansion. As space grows, more dark energy comes into existence, further accelerating the process. The universe is not just expanding, it is being pushed apart from within. The implications of this discovery were profound. An accelerating universe has a fundamentally different future from one that expands at a steady rate. Over vast timescales, acceleration changes not only distances, but the very structure of reality. As expansion continues, galaxies drift farther apart. Clusters that were once gravitationally bound begin to isolate themselves. Eventually, only the local group of galaxies remains visible to any given observer. Beyond that, distant galaxies fade from view, their light stretched to wavelengths too long to detect. This process does not happen suddenly. It unfolds over tens of billions of years. Stars continue to form, galaxies continue to evolve, and life, where conditions allow, may still arise. But the overall trend is irreversible. The universe is becoming larger, emptier, and colder. Expansion has a direct effect on temperature. As space stretches, radiation loses energy. The cosmic background light, once a blazing remnant of the Big Bang, has already cooled to just a few degrees above absolute zero. In the far future, it will cool even further, approaching a uniform, nearly undetectable glow. This gradual loss of heat marks the beginning of what scientists call the thermodynamic decline of the universe. Energy differences, which drive all processes, from star formation to chemical reactions, become less pronounced. With fewer gradients, fewer processes can occur. Gravity resists this trend on smaller scales. Stars and galaxies remain bound for immense periods of time. However, gravity is a local force while dark energy operates on the largest scales. Over enough time, expansion wins. The accelerating universe is not heading toward a dramatic collapse or fiery destruction. Its path is quieter, colder, and more subtle. The danger lies not in sudden annihilation, but in slow isolation. Each region of space becomes increasingly cut off from the rest, evolving toward its own isolated future. This scenario sets the stage for one of the most widely accepted endings of the cosmos, the gradual freezing of all activity. A universe where stars exhaust their fuel, galaxies drift apart, and darkness expands without resistance. The expansion that once allowed structure to form now works against it. The same process that gave rise to galaxies ultimately ensures their separation. In this way, cosmic expansion carries within it the seeds of its own undoing, not through destruction, but through dilution. As the universe grows ever larger, it also grows ever quieter. The next chapters of its story are not written in explosions or collisions, but in the slow fading of light and the relentless march toward cold. This is the road that leads to the first great ending, a universe that does not die in fire or collapse, but slowly loses the ability to change at all. Among all proposed endings of the universe, the Big Freeze is considered the most conservative and the most likely by modern cosmology. It does not require exotic physics or sudden changes in natural laws. Instead, it emerges naturally from what is already observed, an expanding universe dominated by dark energy and governed by the laws of thermodynamics. The Big Freeze describes a future in which the universe expands forever, growing colder, darker, and more dilute with time. In this scenario, no final catastrophe occurs. There is no moment of destruction. The end arrives gradually, stretched across unimaginable spans of time, until all meaningful activity comes to a halt. At the heart of this process lies the second law of thermodynamics. In any closed system, entropy, a measure of disorder, tends to increase. Energy spreads out, differences in temperature diminish, and systems move toward equilibrium. The universe, on the largest scale, appears to be such a system. Today, the cosmos is far from equilibrium. Stars burn hot in the cold vacuum of space. Galaxies shine against a dark background. These contrasts allow structure, motion, and life to exist. But expansion relentlessly erodes these differences. As space grows, matter becomes increasingly dispersed. Gas clouds thin out, making the formation of new stars more difficult. Existing stars continue to burn through their nuclear fuel, converting hydrogen into heavier elements and releasing energy in the process. Once that fuel is exhausted, stars fade. The first to disappear are the most massive stars. They live fast and die young, exploding as supernovae and leaving behind neutron stars or black holes. Smaller stars, like red dwarfs, burn their fuel much more slowly. Some of them may shine for trillions of years, long after galaxies like the Milky Way have changed beyond recognition. Eventually, even the longest-lived stars reach the end of their lives. Without nuclear reactions to sustain them, they cool into dim stellar remnants. White dwarfs, neutron stars, and black holes. The universe enters an era dominated not by light, but by the faint afterglow of once luminous objects. Star formation does not cease suddenly. It declines gradually as usable gas is consumed or dispersed. Over time, galaxies become collections of aging stars and stellar corpses, orbiting in increasingly empty space. As expansion continues, galaxies drift farther apart. Regions of space become isolated, unable to exchange matter or energy with distant regions. Each cosmic island evolves alone, cut off from the rest of the universe by the accelerating expansion of space. Temperature continues to fall. The cosmic background radiation cools toward absolute zero. With fewer energetic particles and fewer interactions, processes slow dramatically. Chemical reactions become rare. Complex structures break down. In the far future, the universe approaches a state known as heat death. In this condition, energy is evenly distributed, and no work can be extracted from it. Without energy gradients, nothing can change in a meaningful way. Time may continue to pass, but events become indistinguishable from one another. Black holes, once thought to be eternal, also participate in this slow decline. According to quantum theory, they emit an extremely faint radiation, now known as Hawking radiation. Over immense timescales, far longer than the current age of the universe. Black holes lose mass and eventually evaporate completely. When the last black hole disappears, the universe reaches a new level of emptiness. What remains is a thin bath of low-energy particles and radiation, spread across an ever-expanding space. No stars, no galaxies, no structure, only near uniformity. This final state is not a dramatic ending, but a silent one. The universe does not collapse or explode. It simply runs out of ways to change. Entropy reaches its maximum. Complexity vanishes. In the Big Freeze scenario, the universe does not die in a moment. It fades. The lights go out one by one, separated by trillions of years. The end is not marked by destruction, but by the absence of anything left to destroy. Yet even this seemingly final state raises questions. Is heat death truly the end? Or could unknown physics, hidden in the quantum fabric of space, allow something new to emerge from the cold and dark? The Big Freeze represents the most patient ending imaginable, a conclusion written not in violence, but in exhaustion. It is the fate of a universe that continues expanding, slowly surrendering its energy to the infinite. Stars are the engines of the universe. They are the primary sources of light, heat, and heavy elements, shaping the structure of galaxies and making life possible. As long as stars exist, the cosmos remains dynamic. When they begin to disappear, the universe enters a fundamentally different phase of its history. In the present era, stars are abundant. Galaxies glow with billions or even trillions of them, forming vast luminous systems bound by gravity. But this era is temporary. Star formation depends on a finite supply of cold gas, and that supply is steadily diminishing. Over time, the raw material required to form new stars is consumed. Gas is locked away inside stars, expelled by stellar winds, or scattered by supernova explosions. As galaxies age, their ability to produce new stars declines. Eventually, the birth rate of stars falls below the rate at which they die. The most massive stars are the first to vanish. They burn through their nuclear fuel at an extraordinary pace, shining intensely for only a few million years before collapsing. Their deaths are violent, releasing immense energy and forging heavy elements. These explosions briefly enrich the universe, but they also accelerate the depletion of star-forming material. Smaller stars live far longer lives. Sun-like stars can shine for tens of billions of years, while the smallest red dwarfs may persist for trillions. For an incomprehensibly long time, these faint stars become the last sources of visible light in the universe. As the ages pass, galaxies change in appearance. Spirals lose their bright arms, becoming dim and red. Elliptical galaxies fade as their stellar populations grow older. The universe becomes dominated by long-lived, low-mass stars and stellar remnants. Eventually, even red dwarfs exhaust their fuel. When nuclear fusion ceases, stars no longer generate energy. They cool and collapse into dark remnants. White dwarfs glow faintly at first, then slowly fade. Neutron stars, incredibly dense and compact, emit diminishing radiation. Black holes remain, silently dominating the mass of galaxies. At this stage, the universe enters what can be called the era of darkness. Light becomes rare. Night becomes absolute. The sky, once filled with stars, is almost completely black. Gravitational interactions continue, but they too become less dramatic. Over vast timescales, stellar remnants interact, collide, or are ejected from galaxies. Some fall into black holes, increasing their mass. Others drift alone through intergalactic space. Galaxies themselves begin to dissolve, not through explosions, but through slow gravitational encounters. Stars and remnants are gradually stripped away, leaving behind sparse, ghostly systems. The loss of starlight has profound consequences. Without stars, there are no stable sources of energy capable of supporting complex structures. Planets freeze. Any remaining forms of life, if they exist at all, must rely on diminishing and increasingly exotic energy sources. As the last stars fade, the universe crosses an irreversible threshold. The age of illumination ends. From this point forward, The cosmos is defined not by creation, but by decay. Yet even in darkness, time continues to pass. Black holes grow through mergers and accretion, becoming the most dominant objects in existence. Their influence shapes the long-term future of the universe. The extinction of stars does not mark the immediate end of all activity. It marks the beginning of a far longer, quieter chapter. A chapter in which gravity and entropy govern a universe almost entirely devoid of light. The story of the cosmos does not end when the stars go out. It merely becomes harder to see. Long after the last stars have faded, the universe does not become completely static. Beneath the apparent stillness, slow and subtle processes continue to unfold. These processes operate on timescales so vast that they challenge human comprehension. Among them is the possible decay of matter itself. Atoms are often perceived as permanent building blocks of reality. In everyday experience, they appear stable and unchanging. Yet modern physics suggests that this stability may be temporary. According to many theories beyond the standard model of particle physics, even the proton, the core of most atoms, may not be truly eternal. Proton decay, if it occurs, is an extraordinarily rare process. Current experiments have not yet observed it, but they have established lower limits on how long protons can survive. These limits extend beyond 10^3 years, vastly exceeding the current age of the universe. If proton decay is real, then all ordinary matter is ultimately doomed. In a universe where proton decay occurs, the implications are profound. Over unimaginable periods of time, atoms would slowly fall apart. Hydrogen, carbon, oxygen, and all elements would gradually disintegrate into lighter particles. The solid structures that once defined planets, stars, and living beings would lose their coherence. White dwarfs, composed primarily of electron-degenerate matter, would be among the last structured objects to persist. Without fusion or external energy, they would slowly cool, becoming dark, inert spheres. Yet even these remnants would not be immune to the decay of matter. As protons vanish, atomic nuclei destabilize. Molecules cannot exist without atoms, and chemistry becomes impossible. The universe transitions from a place where matter forms complex structures to one dominated by elementary particles drifting through space. Neutron stars present a similar fate. Despite their extreme density and gravitational strength, they rely on the same fundamental particles as all other matter. Over time, proton decay would undermine even their internal structure, reducing them to diffuse clouds of particles. If proton decay does not occur, matter still faces other forms of transformation. Quantum tunneling may allow even the most stable configurations of matter to rearrange themselves. Over immense timescales, white dwarfs and neutron stars could collapse or transform, not through violence but through probability. Planets, once frozen and lifeless, continue to orbit stellar remnants until gravitational interactions disrupt them. Some are ejected into interstellar space. Others spiral inward and are consumed by black holes. The organized architecture of planetary systems dissolves. As matter decays or disperses, the universe becomes increasingly simple. Complexity, once abundant, gives way to uniformity. Energy levels drop. Interactions become rare. In this distant future, the dominant forms of matter are lightweight particles. Electrons, positrons, neutrinos, and photons. These particles carry little energy and interact weakly, passing through space almost without notice. Time itself takes on a different character. With few events and fewer interactions, change becomes nearly imperceptible. The universe approaches a state where cause and effect still exist, but their consequences are minimal. The decay of matter marks another step toward the thermal death described in earlier chapters. Without stable atoms, there can be no structures capable of storing information or sustaining processes. Memory, in any physical sense, fades. Yet even as matter disintegrates, black holes remain. They are largely unaffected by proton decay, governed instead by gravity and quantum mechanics. In the long run, they become the last significant repositories of mass and structure in the universe. The fate of atoms is not merely a footnote in cosmic history. It represents the loss of the very ingredients from which complexity arises. When atoms disappear, so does the possibility of anything resembling the universe as it is known today. This slow erasure of matter brings the cosmos one step closer to a state where structure, chemistry, and history itself dissolve into near-perfect simplicity. Not all endings of the universe are slow and quiet. While the Big Freeze envisions a gradual fading into darkness, another scenario proposes a far more violent fate, one in which the expansion of the universe does not merely continue, but accelerates without limit. This scenario is known as the Big Rip. The Big Rip emerges from a particular interpretation of dark energy. If dark energy is not constant, but instead grows stronger over time, its repulsive force could eventually overwhelm all other forces in nature. Gravity, electromagnetism, and even the forces binding atoms together would ultimately fail. In this model, expansion does not simply separate galaxies. It actively tears the fabric of space apart. At first, the effects are subtle. Galaxies drift away from one another faster than before. Large-scale structures lose their cohesion. Clusters of galaxies, once held together by immense gravitational forces, begin to dissolve. Individual galaxies become isolated islands in an ever-expanding void. As acceleration increases, the damage spreads inward. Gravity can no longer hold galaxies together. Stars drift away from their galactic cores. Planetary systems become unstable as the force driving expansion rivals the gravitational pull of stars. Closer to the final stages, the expansion rate becomes catastrophic. Planets are stripped from their orbits. Moons lose their grip on planets. Objects once bound by gravity are pulled apart, not by explosions, but by the stretching of space itself. Eventually, even stars cannot survive. The force pushing space outward exceeds the nuclear forces holding stellar matter together. Stars are torn apart, their plasma scattered across rapidly expanding space. The timeline of the Big Rip is precise and unforgiving. As the end approaches, destruction accelerates dramatically. What took billions of years to unfold now happens in minutes, then seconds. In the final moments, the expansion overwhelms the strongest forces known to physics. Molecules are ripped apart. Atoms lose their structure as electrons are separated from nuclei. Even atomic nuclei disintegrate as the strong nuclear force is overcome. Space itself becomes unstable. Distances grow infinitely large in an infinitesimal amount of time. The concept of location loses meaning. There is no longer a coherent universe, only fragments of reality being pulled beyond any possibility of interaction. Unlike other endings, the Big Rip has a defined moment of termination. Time, as experienced within the universe, effectively ends. No observer could witness the final instant, as the processes of perception and causality would fail before the conclusion is reached. The Big Rip is not merely the destruction of matter. It is the destruction of structure at every scale. From galaxy clusters to subatomic particles, nothing remains intact. The universe does not cool into silence. It is violently erased. This scenario depends entirely on the nature of dark energy. Current observations suggest that dark energy behaves like a constant force, which would make the Big Rip unlikely. However, the true nature of dark energy remains unknown. A slight deviation from current measurements could drastically alter the fate of the cosmos. The Big Rip represents the most extreme consequence of unchecked expansion. It is a universe undone not by collapse or exhaustion, but by excess, too much space, too much separation, too much acceleration. If the Big Rip awaits, the end will not come quietly. It will arrive as the ultimate tearing of reality itself, a moment when the universe can no longer hold together in any meaningful way. For much of the 20th century, the dominant vision of the universe's fate was not endless expansion, but collapse. According to this scenario, known as the Big Crunch, the expansion of the universe would eventually slow, stop, and reverse. What began with the Big Bang would end in a mirror image of its birth, a final catastrophic contraction. The idea of the Big Crunch arises naturally from gravity. Matter attracts matter. On sufficiently large scales, gravity acts as a cosmic counterforce to expansion. If the total density of matter and energy in the universe were high enough, gravitational attraction could overcome expansion and pull everything back together. In such a universe, expansion is only a temporary phase. Galaxies initially move apart, but their motion gradually slows. Over billions of years, the outward momentum fades. The cosmic expansion reaches a halt, a moment sometimes called the turnaround point. After that moment, the direction of cosmic history reverses. Space itself begins to contract. Distances between galaxies shrink. Structures that were once drifting apart start moving toward one another. The night sky grows brighter as galaxies approach, their light becoming more intense and frequent. As contraction accelerates, galaxies collide and merge at an increasing rate. Star formation briefly surges as gas clouds are compressed. The universe enters a violent and chaotic era, filled with radiation, shocks, and gravitational upheaval. Temperatures rise. Energy densities increase. The calm, cold future predicted by the Big Freeze is replaced by growing heat and compression. The universe becomes smaller, denser, and more energetic with every passing moment. On shorter timescales, planetary systems are destabilized. Stars are torn from their orbits by gravitational encounters. Black holes grow rapidly as they consume surrounding matter and merge with one another. As contraction continues, the distinctions between individual galaxies disappear. The cosmos becomes a dense, glowing mass of matter and radiation. Space no longer offers vast emptiness. Everything is close, crowded, and intensely interactive. Eventually, the universe approaches conditions similar to those at its beginning, but in reverse. Temperatures soar to extreme levels. Atomic structures cannot survive. Matter dissolves into fundamental particles. Radiation dominates. In the final stages, even the known laws of physics may cease to function in any recognizable way. Gravity becomes overwhelming. Quantum effects dominate large scales. Time and space lose their familiar meanings. The Big Crunch represents a true ending in the classical sense. Unlike the Big Freeze, it does not stretch indefinitely into the future. It culminates in a finite moment, a final collapse in which all matter and energy are compressed into an unimaginably small volume. What happens at that ultimate point remains unknown. Some theories suggest a singularity, similar to the one associated with the Big Bang. Others propose that the collapse could trigger a new expansion, a rebirth of the universe in a cyclic process. This possibility leads to the concept of a cyclic cosmos, where universes are born, expand, collapse, and are reborn again and again. In such models, the Big Crunch is not an end, but a transition. Modern observations, however, suggest that the density of matter in the universe is too low for a Big Crunch to occur under current conditions. The accelerating expansion driven by dark energy appears to work against any future collapse. Yet the Big Crunch remains a powerful reminder that cosmic fate depends on delicate balances. A slight change in fundamental parameters, density, energy, or physical laws could radically alter the future. The Big Crunch is the story of a universe undone by its own gravity, a cosmos that turns inward, erasing distance and structure, collapsing back toward the state from which it emerged. It is an ending defined not by emptiness, but by excess, too much matter, too much gravity, too much convergence. Among all possible endings of the universe, there is one that stands apart for its suddenness and inevitability. It does not depend on the slow passage of time, the fading of stars, or the gradual expansion of space. Could occur tomorrow or never at all. This scenario is known as false vacuum decay. To understand this possibility, it is necessary to reconsider what is meant by empty space. In classical thinking, a vacuum is nothingness. In modern physics, it is anything but. Even the emptiest regions of space are filled with quantum fields, fluctuating with energy. These fields define the fundamental properties of reality. According to quantum field theory, the universe may exist in a metastable state, a false vacuum. In this condition, the energy of empty space is not at its absolute minimum, but merely at a local minimum. The universe appears stable, yet it rests on a delicate balance. A true vacuum would represent a state of lower energy. If a transition from the false vacuum to the true vacuum were to occur, it would release energy and fundamentally alter the laws of physics. This transition would not spread gradually. It would occur through the formation of a vacuum bubble, a region where space has shifted into the true vacuum state. Once formed, this bubble would expand at nearly the speed of light. Inside the bubble, the fundamental constants of nature would change. The strengths of forces, the masses of particles, and the behavior of fields could be entirely different. Atoms as they exist today might be impossible. Chemistry would cease to function. Matter would not survive. The most unsettling aspect of false vacuum decay is its invisibility. There would be no warning, no build-up, no observable signal approaching from a distance. The bubble would arrive at the speed of light, making detection impossible before annihilation. For any observer within the universe, the end would be instantaneous. Time, space, and structure would simply cease to exist in their familiar forms. From an external perspective, if such a perspective were meaningful, the affected region would be erased and replaced by a new, alien reality expanding outward. The probability of false vacuum decay is believed to be extremely low. The current age of the universe suggests that if such decay is possible, it is exceedingly rare. Yet rare does not mean impossible. Given infinite time, even the most improbable events may occur. Some theories suggest that high-energy processes, such as those occurring during cosmic inflation or in extreme astrophysical environments, could trigger vacuum decay. Others propose that decay is purely spontaneous, arising from random quantum fluctuations. The discovery of the Higgs boson added a new dimension to this discussion. Measurements of its properties suggest that the universe may indeed be metastable, balanced precariously between stability and decay. While this does not imply imminent danger, it reinforces the idea that the current state of the universe may not be permanent. Unlike the Big Freeze or Big Crunch, false vacuum decay does not offer a prolonged narrative. There is no long decline, no observable transformation. One moment the universe exists, the next it does not, at least not in any recognizable form. This scenario challenges the notion of cosmic predictability. It suggests that the end of everything may not be written in distant futures measured in trillions of years, but embedded in the quantum fabric of the present moment. False vacuum decay represents an ending without witnesses, without ruins, and without memory. No structures survive to record what came before. The universe does not age into its death. It is replaced. In this sense, false vacuum decay is not merely an ending. It is a reset of reality itself, governed by laws beyond current understanding. Whether such an event will ever occur remains unknown, but its possibility serves as a reminder that even the most stable-seeming cosmos may rest on hidden instabilities, waiting silently within the depths of quantum space. All scenarios describing the end of the universe eventually confront a deeper question, one that goes beyond stars, matter, and energy. What happens to time itself? Is time an eternal backdrop against which cosmic events unfold, or is it a property that can fade, fracture, or cease altogether? In everyday experience, time appears absolute. Moments follow one another in a clear sequence. Causes precede effects. Past, present, and future seem distinct and irreversible. Yet modern physics has revealed that time is far more fragile than intuition suggests. According to relativity, time is inseparable from space. Together, they form spacetime, a dynamic structure shaped by matter and energy. Gravity is not merely a force acting within spacetime. It is the curvature of spacetime itself. When spacetime changes, time changes with it. In extreme cosmic conditions, the familiar flow of time breaks down. Near black holes, time slows dramatically. For a distant observer, clocks near the event horizon appear to freeze. Inside, according to theory, spacetime becomes so distorted that time and space exchange roles. Movement toward the future becomes as unavoidable as movement toward a location. As the universe evolves toward its end, such distortions may become widespread. In a collapsing universe, approaching a big crunch, increasing density and gravity could cause time to behave erratically on cosmic scales. Intervals lose meaning, sequences blur. In a universe dominated by expansion, the opposite problem emerges. As space stretches endlessly and matter thins out, events become increasingly rare. Time continues to pass mathematically, but nothing happens to mark its passage. Without change, time loses physical significance. This leads to a profound question. Does time exist if nothing occurs? In the far future of a heat-dead universe, where particles drift in near-perfect equilibrium, there are no clocks in any meaningful sense. No processes repeat. No systems evolve. Time may still be defined by equations, but it has no observable manifestation. Causality, the relationship between cause and effect, also becomes uncertain. In quantum physics, causality is already probabilistic rather than deterministic. Events do not follow strict chains. They occur within ranges of likelihood. At cosmic extremes, even this probabilistic causality may fail. If the universe enters a state where spacetime itself is unstable or fragmented, the concept of cause preceding effect may lose coherence. Some theories suggest that near the end of the universe, spacetime could break into disconnected regions. In such a cosmos, there is no global timeline, only isolated local sequences, each evolving independently. Other models propose that time itself may have a finite extent. Just as the universe had a beginning in time, it may also have an end. Beyond that boundary, the concept of after becomes meaningless. In scenarios like false vacuum decay, time does not slow or stretch. It simply ends for the affected region. There is no transition, no final moment experienced by an observer. The timeline is cut short. The death of time is not necessarily dramatic. It may arrive quietly, as a gradual loss of distinction between moments. When the universe can no longer support change, time becomes redundant. This challenges one of humanity's deepest assumptions, that time is the fundamental stage upon which existence unfolds. Instead, time may be an emergent property, arising only when the universe is sufficiently complex. If that complexity fades, time fades with it. The end of the universe, then, may not be marked by darkness or destruction, but by stillness so complete that even duration ceases to matter. A cosmos without clocks, a reality without before and after. In such a state, asking what happens next becomes a meaningless question. The story does not continue, not because it concludes, but because the framework that allows stories to exist is gone. This is the quietest possible ending, not the death of matter or energy, but the dissolution of sequence itself. The idea that the universe may end raises an equally compelling counter-question. Could an ending also be a beginning? While many cosmological models describe final states of exhaustion, collapse, or erasure, others suggest that the universe may possess the capacity to renew itself. In these theories, the end is not absolute. It is transitional. One of the oldest concepts of cosmic rebirth is the cyclic universe. In this framework, the cosmos undergoes an endless sequence of expansions and contractions. Each cycle begins with a Big Bang, like event, and ends with a collapse resembling a big crunch. The end of one universe becomes the seed of the next. In such models, time has no ultimate beginning or end. Instead, it stretches infinitely in both directions through repeating cosmic epochs. Matter and energy are recycled, though not necessarily in identical forms. Each cycle may differ slightly from the last. Modern physics has revisited cyclic ideas with renewed interest. Advances in quantum gravity and string theory suggest that spacetime itself might avoid true singularities. Instead of collapsing into an infinitely dense point, the universe could rebound. This rebound is often referred to as a big bounce. In a big bounce scenario, the universe contracts to an extremely dense state, but quantum effects prevent complete collapse. At a critical threshold, gravity becomes repulsive, triggering a new expansion. The Big Bang, in this view, is not the beginning of everything, but the continuation of an earlier phase. Another rebirth concept arises from inflationary cosmology. According to some models, inflation, the rapid expansion that occurred shortly after the Big Bang, may be an ongoing process. While inflation ends locally, it continues elsewhere, producing countless pocket universes. In this multiverse picture, our universe is just one bubble among many. Each bubble has its own beginning, physical constants, and fate. When one universe ends through heat death, collapse, or vacuum decay, others may continue unaffected. Some theories even suggest that the death of one universe could trigger the birth of another. Energy released during extreme events, such as vacuum decay or black hole evaporation, might seed new regions of spacetime with their own expansions. Black holes themselves have been proposed as potential gateways to new universes. In certain speculative models, the interior of a black hole does not end in a singularity, but instead connects to a new expanding spacetime. From the outside, the black hole appears as a grave. From the inside, it may be a womb. If this is true, then the universe could be constantly giving birth to new universes through the deaths of massive stars and the mergers of black holes. Each generation spawns the next, hidden beyond event horizons. The possibility of rebirth reframes the concept of cosmic death. An ending may not signify annihilation, but transformation. What appears final from one perspective may be the origin of something entirely new from another. However, these ideas remain speculative. They lie at the frontier where physics approaches philosophy. There is currently no experimental evidence confirming cyclic universes, bounces, or cosmic reproduction. Yet, the mathematical consistency of these models keeps them within serious scientific discussion. The appeal of cosmic rebirth is not emotional optimism. It arises from attempts to resolve deep inconsistencies in physical theory, such as singularities, information loss, and the arrow of time. Rebirth offers a way to extend the story without violating fundamental principles. Still, even if rebirth occurs, it does not guarantee continuity. A new universe may share no information, structure, or memory with its predecessor. From within, it would appear as a complete beginning, unaware of what came before. In that sense, rebirth does not negate endings. It merely places them within a larger, more complex framework. The universe as it is known may still truly end, even if reality itself continues. The question then becomes not whether the cosmos can begin again, but whether beginnings and endings are meaningful concepts at the deepest level of existence. Perhaps the universe is not a single story with a start and a finish, but an ongoing process, one that reshapes itself endlessly, indifferent to notions of finality. As the universe approaches its possible endings, another question emerges, one that reaches beyond matter, energy, and even time. What happens to information? Does the universe remember its past, or is all memory ultimately erased? In physics, information is not an abstract concept. It is encoded in the arrangement of particles, the states of fields, and the correlations between systems. Every structure, from a galaxy to a living brain, stores information simply by existing in a particular configuration. Memory, in this sense, is physical. The fate of information has long been a subject of intense debate, especially in the context of black holes. For decades, black holes were thought to destroy information completely. Anything that crossed the event horizon appeared to vanish forever, leaving behind only mass, charge, and spin. This idea conflicted with the fundamental principles of quantum mechanics, which suggest that information cannot be destroyed. The resulting paradox forced physicists to reconsider their understanding of reality. If information truly disappears, then the past becomes unrecoverable in a fundamental way. Cause and effect lose their strict meaning. The universe forgets. Modern theories suggest that information is not destroyed, but transformed. In the case of black holes, information may be encoded in subtle correlations within Hawking radiation or preserved on the event horizon itself. Yet even if information survives locally, its long-term fate remains uncertain. In a universe heading toward heat death, information faces a different threat. As energy differences vanish and systems reach equilibrium, the physical structures that encode information dissolve. Without stars, planets, or stable matter, there are no mechanisms to store or process memory. Bits of information become indistinguishable from one another. Order fades into randomness. The distinction between one state and another loses meaning. Information may still exist mathematically, but it becomes inaccessible and irrelevant. This loss of accessible information has profound implications. History as a physical record disappears, No traces remain of galaxies, civilizations, or events. The universe does not merely become empty, it becomes forgetful. In cyclic or rebirth scenarios, the question becomes even more complex. If a new universe emerges from the collapse or transformation of an old one, does any information carry over? Or is each cycle a complete reset? Some models suggest that information could survive in altered forms, embedded in the fundamental parameters of a new cosmos. Others propose that each rebirth erases all prior structure, rendering the past completely inaccessible. The arrow of time itself is closely tied to information. Time appears to flow in one direction because entropy increases and information about the past is retained, while information about the future is not. If memory vanishes, the arrow of time may vanish with it. In a universe without memory, the distinction between past and future collapses. Events do not accumulate into history. They leave no trace. Meaning, which depends on continuity and context, becomes impossible. From a human perspective, this is perhaps the most unsettling aspect of cosmic endings. It is not merely that life ends, or that stars go dark. It is that everything that ever happened becomes irrelevant, unrecorded, and unremembered. Yet physics offers no special protection for meaning. The laws that govern particles and fields are indifferent to memory, identity, and significance. Information survives only as long as the universe can support structures capable of encoding it. In this sense, memory is a temporary phenomenon, an emergent feature of a universe far from equilibrium. As equilibrium approaches, memory fades. The fate of information reveals a deeper truth about existence. The universe does not preserve its story by default. Continuity is not guaranteed. Persistence is conditional. When the final stages arrive, whether through freezing, collapse, tearing, or transformation, the last traces of order may vanish. What remains may be a reality without records, without witnesses, and without context. The end of the universe, then, is not only a physical conclusion. It is the end of remembrance. Every scenario describing the end of the universe, no matter how different in detail, converges on a single truth. Change cannot continue forever. Whether the cosmos fades into cold equilibrium, tears itself apart, collapses inward, or is replaced by a new reality, there comes a point beyond which nothing familiar remains. The final moment of the universe is not defined by a single image. There is no universal last scene. In some futures, the end is stretched across eternity, diluted into stillness. In others, it arrives suddenly, without warning, erasing everything in an instant. The nature of the ending depends entirely on the laws that govern reality, and on whether those laws themselves remain stable. In a slowly dying universe, there is no final explosion. The last stars have long since gone dark. Black holes have evaporated. Matter has decayed or dispersed into low-energy particles. What remains is a thin, almost uniform sea of radiation and elementary particles drifting through an endlessly expanding space. In such a cosmos, there is no final event. Nothing happens to mark an ending. The universe does not collapse or vanish. It simply loses the ability to do anything at all. The final moment is not a moment, but a condition. In more violent scenarios, the end is sharp and absolute. The Big Rip tears all structures apart, leaving no time for transition. False vacuum decay replaces reality itself at the speed of light. In these cases, the final moment is not experienced, cannot be observed. The processes required for observation cease before the end occurs. There are also endings that fold back into beginnings. A collapsing universe may rebound. A black hole may give rise to a new expansion. In these visions, the final moment is not an endpoint, but a threshold, a boundary beyond which the current form of reality cannot persist. Yet even in rebirth, there is loss. Whatever comes next does not preserve the details of what came before. Galaxies, stars, and histories do not survive the transition. Continuity is broken. The universe begins again without memory. From within the cosmos, there is no external perspective. No witness stands outside the universe to observe its final state. The universe is both the stage and the audience. When the stage disappears, so does the observer. The idea of a final moment challenges human intuition. Experience is built on sequences, on one thing following another. But the end of the universe may not allow for sequence at all. Time may dissolve. Causality may fail. The concepts that define after and before may no longer apply. In this sense, the end of the universe is not an event that happens in time. It is the point at which time itself loses meaning. What remains after that point is not darkness, emptiness, or silence in any familiar sense. Those are still concepts that depend on contrast and perception. Without structure, without observers, even silence becomes an empty word. The universe does not conclude with a statement. It does not explain itself. It does not justify its existence. It simply reaches the limit of what it can be. And yet, the fact that such an ending can be contemplated at all is remarkable. For a brief moment in cosmic history, the universe produced minds capable of asking how it would end. In doing so, it became aware of its own impermanence. That awareness does not change the outcome. The universe is indifferent to observation, but it gives meaning to the present. Everything that exists does so within a narrow window between origin and extinction. The final moment, whatever its form, does not erase the fact that the universe existed. It does not negate the stars that once burned, the galaxies that once formed, or the questions that were once asked. The universe may end without memory, without witnesses, and without legacy. But for a time, it was complex enough to know that it would not last. And in that fleeting awareness, the story of the universe was complete.